So, good afternoon. I think it's time to start our last session for today. So we have three panelists or three presenters, and this is actually, so the last one was focused on innovation, and here we have a wider range actually of topics, so we'll hear more about the studies regarding both science and innovation. And it's a great pleasure actually to have such a varied and really interesting and complementary group of speakers today. So we will start with Daniel McFarland. He is a professor at Stanford University in the Graduate School of Education. He was a director of the Stanford Center for Computational Social Science. And in general, he uses large academic corpora to develop models of intellectual movements and scholar migration. So he's really working a lot with the big data, social networks, and language modeling. So, Dan.
Thanks. And just really quick, what I'm going to present today is just a little chunk of the larger set of things we're doing with lots of different projects and lots of different models. What I wanted to focus on was taking one thing that I don't think many people consider very often, and that's dissertations. I know that sounds kind of drab, but let me explain why. It's about intellectual lineages. And intellectual lineages, there's a lot of reason why you want to study them. In a lot of my other work, we study fads and fashions of research, hype cycles of where resources push people to kind of develop a sub-language of research that rises and falls. And it's triggered by a lot of micro-mechanisms and the like. However, there's these long-term kinds of mechanisms in academia that hold. And one of them has to do with the training of students, and particularly the workforce of faculty. And their research pretty much defines a great deal of the agenda that we have going forward. They have these long careers. They have all these descendants. And some of them have more descendants than others. And this is where we have a faculty of production, a birth system, right? Where certain groups are outpacing others in terms of their rates of birth, their number of birth, and their expansion in academia. And this is kind of going to dictate in many regards where innovation's arising, right? And so the focus today, what I'm going to try to talk about is reproductive success of scholars. And we'll see if any of you feel the pinch of this talk. So I'm going to keep it pretty descriptive, too. I'm going to keep it simple. I haven't figured everything out. We have this huge data set, and we're trying to develop scalable models with predictive and causal kinds of analysis. So it's building. And it's really weird to have cameras going. I'm not used to it. Maybe you were. I'm not. Sorry, which PhDs become faculty advisors, the first question, and then which PhDs go on to have the largest intellectual lineages? By this I mean not only children, but children's children, like so grandchildren who become faculty themselves, who then have other faculty. Who's producing this most, right? And where are the biases out there? And so one of the obvious questions is there inequality? And we have all kinds of obvious things like about the field. Is it STEM or non-STEM? Which one has a bonus there? Our disciplinarity versus interdisciplinarity. I know some of you will be interested in that. What's the benefit of either route if you do a dissertation that spans areas or stays in them? Institution-wise, do elite institutions have this huge benefit or not? And is it what kind of benefit? And do you see it again with private and public? And actually those two are very similar, we'll find. And then finally, just persons. I mean, one of the key attributes that we are concerned about in science is gender, right? And the lack of representation of women in a lot of fields. So these are the kind of things we can start to look at. And here's the kind of data set that I'm going to talk about. So what we've done is we've collected data off ProQuest, which stores millions of dissertations. And in those dissertations, they show things like, as you can see, here's an example at the top. Some guy, Dan McFarland, got a degree in sociology and education. His advisor was Paget. He wrote this thesis. Then he goes on to have a student, Sarah Ramage, who's in 2 other fields, and then she goes on to have a student, Jenny Doe, in a different field. And so you have these lineages, right? These aren't real. I kind of made it up, except for the first part. But the point is that you have these kinds of descents, right? And they have different ranges of time. You can think of whether your childbearing age, et cetera. I mean, as an intellectual, I care about this, whether I'll have any kind of trace after me. And I think a lot of people out there do in terms of your kind of legacy. Now, we also linked this up with NRC rankings from 2011, as well as where it's missing for certain fields like education, business, and law. We do it for US News and World Report. So just to give you an idea, I know big data can be wrong, and it's found data. And that's a big problem. 100 years of social science research has taught us that sampling matters, right? So one of the things I care about is knowing, is this data representative? And so I went to the NCAS site, looked at all their representation of the survey of doctoral theses, doctoral students that they've had between 2002 and 10. We cover about 71%. So it's not perfect. And then what I did was I looked to see, well, what kind of missing do we have? So I went to the Stanford library, just one sample, to see what's missing. We're 5% off at Stanford. I thought it would be more because I thought people were holding back their thesis from posting it because they wanted a patent. But you would think Stanford would be the one place where that would really happen. So it's not really that. What's happening is people who don't want to go on to academe aren't posting. So if there's a bias in my data, it's a little bit about in that direction is the assumption here. So we do have some kind of bias that we need to consider, but nonetheless, the nice thing about this data is it goes back much further than NCES, and we start to see legacies and traditions and lineages. So real quick, just some simple plots. This is the growth in dissertations over the last 30 years. It's doubled from 20,000 to 40,000 dissertations a year. So that's quite a bit of an intellectual production force change, right? In addition, if you start to plot this by area, you'll start to see that certain areas are outpacing others. You'll notice at the bottom here we have biological and health sciences seem to have the biggest growth. Physical and math and engineering seem to too. So there's kind of growth across the board, but certain areas seem to be expanding a little more rapidly. If I look at female and male, you'll notice that females are growing as a representative population. Male, by the way, we had to do this with a name recognition package where we tried to automatically extract out gender, and it turns out it's pretty reliable except for Asian names. So you can think of it because of if we had Chinese characters, we could get gender better, but then again, not always, so on it goes. But it's kind of nice because you start to see actually international names growing, right? So it's nice to see kind of a trend there, but you see that there is kind of representation that's shifting. And then by rank, in terms of whose dissertations, this is the top 10 institutions in each field. They characterize a good chunk, but definitely not everybody, right? So this is spanning quite a few fields. Probably, I forgot earlier, we have something like all fields in science, and then we have something like 340 institutions here, and they're all US based. So really quick, these are the things I want to look at. I want to look at how do we capture reproductive success? So the reproduction likelihood. So if you're a student who graduates, what's your chance of ever having your own advisee? Meaning you get a job and reproduce. Okay? Only 5% overall ever do that, of all graduates getting a PhD. The time to reproduction. Now this varies greatly. Some people are faster at coming to having a child versus others not. Okay? I have to use this metaphor because it's just easier for me and maybe you. So some fields are really slow, others are fast, right? And that can lead to kind of expansion of some fields over others. The last is some fields have lots of lineage, meaning they have descendants among descendants among descendants, others die out, right? And so what we find is you have about 10, 4 to 10 or 12, that kind of range of number of descendants if you reproduce. So the implication here is that long-term knowledge growth, we think, is really highly related to kind of these demographic kinds of population trends and the producers of intellectual knowledge. So just to give you an idea, what we've done here is I've developed a plot where on the y-axis you have the percent likelihood of reproducing. So this is a department which can reproduce at 25%, meaning they'll have 25% of their students will get a student of their own someday. And then we showed the rank orderings, and along here is the time to birth, right? So after graduation, 5 years, you're really quick. Here is 14. And if I can get out of here and go here, I can show you an interactive graph where we can start to see the larger these stars are, the more children they have, right? So it's a bigger bigger lineage. And so what you find is higher ranked institutions are bigger stars, right? They're just larger producers of the intellectual body of workers, right? So this is kind of a clear bias. We don't see it really on the time to birth. So, but if you come over here, you start to see physiology, infectious disease, animal sciences. If I come over here, you start to see engineering. So you start to wonder if there's some kind of, yeah?
What is the top left star?
This one? Caltech. So some of these institutions have smaller departments where they produce, and smaller institutions. Caltech is one, particularly for engineering, that shows up. So I can send out that later. Where do I go to get my... Here's a different representation, though. Come on. Sorry, it's supposed to move on. Go to the, here we go. Here, thank you. Sorry about that. So what you find here is we did it by field, and what you find is engineering's on the left. They produce quickly, lots of children quickly. And then biology, you see a lag. And it's exactly because someone was saying earlier, you go on for this whole thing about postdocs and endless things. And mind you, there's a lot of literature out there in the sociology and history of science where if you have this endless wait for a job, the students will rebel and revolt like they did in Paris in the 60s. So it's whether the biologists will do that, we'll wait and see. Institution-wise, there's a huge amount of inequality in terms of who's representing most of the jobs and most of the children being born. It's all elite institutions. 60% of all of these people are driven by the elite institutions. So huge inequality, and if you look at the flows across them by rank, it's kind of this thing where the top institutions populate all the lower ones in terms of ranking, and then the lower one, there is some flow up, but it's kind of the exception as opposed to the rule. And then if you look at the graph in terms of job flows, where people move across these, you start to see certain ones are actually in the middle. Thankfully, University of Berkeley's in there. For the moment, and hopefully we can sustain those kinds of things. But there is a huge inequality in terms of production. So, great. Well, what corresponds with reproductive success, though? I'm showing you all these cute graphs of inequality. What is actually associated with it? So we have various possible things that are predictive of it. And what I'm going to do is I'm going to do just some initial predictive models, a logistic regression of whether you ever have children, and then a negative binomial, which is just kind of the number, if you do produce children, how many will you produce? And what are factors that contribute to having lots of kids, okay? Or long lineages. So here are the results for the simple thing of whether you ever have a child or not. And so what you're finding is STEM fields have a slight bias. The odds aren't huge, but this is whether the likelihood of any graduate. Most people never reproduce, right? 5% ever. So the likelihoods are 1.25 higher for a STEM field than for, sorry, a STEM field than for a non-STEM. And then males are almost 1.5 times more likely than females. Interdisciplinary is the third, is slightly higher likelihood for reproduction. And then we see the typical rankings that you would expect compared to field or schools that are less than the 50th rank on the NRC or in US News. And then finally, private schools have a similar boost compared to public schools. So the kind of inequalities we'd expect. Now if we look at it over time, not over time, in terms of the number of children they get as well, we see a the kind of continued inequality of this. So it's not just that stem cells are more likely to have a child, but they have more of them. It's not just that women are less likely to have a future advisee, but even when they do, they have fewer of them, okay? And interdisciplinarity have slightly more when they do. And then there's a curious result here of why is the top 50 below the rest in terms of the number of children. And one of the arguments is it's like a teaching college, right? You're more likely to go on to become a professor, perhaps from top 50. But when you do, you might not produce, you might not be, the ones below, the below 50 are an exception, right? And they may be highly productive. So we don't know. We have to look into this a little more. But what the logit and the multinomial, the negative binomial are showing is this lot of compounding inequality of where resources and reproduction arise. That's great, but we have longitudinal data, so we could do all these cool things, right? We can start to say, well, how does this fluctuate over time? And one of the neat things you can do is age, cohort, and period effects, right? Because you can ask, well, does this change for women and men the same way over time, their career? Do we see equalization over the career? Is it just something initial or later? There's various arguments for why, like childbearing or whatnot. Another one could be for the cohort effects. Cohort effects could be like back in the 80s, nobody did interdisciplinary and now they do. That's one possibility. Another one could be the period effects. Maybe interdisciplinary is really cool now, right? And so therefore having someone that's interdisciplinary today in this kind of day and age has some kind of added demand, okay? So these are all feasible. There's many others that we can posit, some of which we might be a fan of more than others. So we can start to plot these, though, and you start to see the inequalities, again, that hold over time. So here's STEM versus non-STEM, and obviously the first 5 years, the first 5 years after you become a faculty or come out of a PhD, you have a very low likelihood of having any children, right? So that's just the period that you're trying to find students. So, but quickly you see STEM outpace non-STEM. So it's pretty stable, though. Another one is the cohort effect, which is a 1980 cohort has had 30 years to produce an advisee, so obviously they have a greater chance. But as you get further down, we start to see some kind of equalization. It's not as clear that it's diminishing, I think, a little bit. If you look over time for the period effect, meaning whether it comes into style or not, you notice that for some reason, an interdisciplinary thesis, someone graduating with one was in higher demand in those periods over others. And that could be because of 9/11 and the defense kind of funding. It could also be something else happened in the 90s. We need to look into it, but there's kind of clear bumps going on. Now when we look at gender, we see kind of stability in the graphs in terms of age over age, the inequality holds. We see it hold in terms of your cohort, so regardless of your cohort, there seems to be a persistent inequality. And then we see it even in terms of the periods that you're in, so the demand kind of effect of those times. When we look at interdisciplinarity, we don't see a strong effect when we start looking at it over time. It's actually something additive over all time periods that we see some kind of contribution, but you do see kind of a little bit of a bump here. So mid-career, about right after tenure, 10 years out, you get a slight advantage into going into interdisciplinary, perhaps because you can afford to. Another is that we see initially, there's in the cohorts in the 80s, it wasn't very popular, but you know there were all these initiatives to do interdisciplinarity in the 80s and 90s, and that might have made those cohorts more likely, so it was unpopular at first and then more popular. And then finally, a kind of a weird result, which we're kind of struggling with, which is this period effect, which is the idea that interdisciplinarity has only now kind of come into fashion in great demand in terms of the students, the people who graduate with an interdisciplinary doctorate. They are suddenly on par now in terms of birthing students at the same rate in these years, the later years. So we have a variety of kinds of effects out there. We see it again with rank. The age effect is consistent where the top rank, the top 10 dominate crazily. We see it again with cohort effects, and we see it again with period effects. So there's a variety of clear inequities occurring in the data for 1 million people out there who have graduated over the last 30 years, which lead you to kind of realize that there's this growing populations in different areas, and they're expanding in certain regions and populating additional kinds of students for a variety of reasons, likely. And we find these basic patterns. Now, the basic thing that we're going to move on to next, and I don't have time to present to you, and we're currently trying to figure it out, is the full model, where we do a multi-level, cross-random age cohort period effect model. And in that, it's quite complicated, and to do it the number and the scale that we have, it's been kind of difficult to get it to run. So we're still working on that, and we're still looking for an instrumental variable. Other people have done things like department size or something like that as a potential instrumental variable for these things that might not predict your likelihoods, but which might predict the independent variables that we're finding as important. We're also trying to find other data from NCES, where they have survey data on students' attitudes when they graduate, as well as kind of funding data from NIH. We're linking right now in NSF to see if the kind of funds you receive facilitate these things, and whether all these factors start to compound the inequities and explain as mechanisms for why they arise. So that's where we are, and that's what I've got. Thanks.
Okay, so thank you, Dan. And I think we'll have, like the previous session, we'll have questions at the end. So the next presenter is Petra Ahrweiler. Petra is the director of the European Academy of Technology and Innovation Assessment and the professor of Technology and Innovation Assessment at Johannes Gutenberg University, Mainz in Germany. Petra actually has done a lot of agent-based modeling and simulations, and she was heavily involved with SKIN project or SKIN model, which is simulating knowledge dynamics and innovation networks. So she will going to share some of that work very soon.
Thank you.
Okay.
All right. Thank you very much for having me here. Thank you for the invite. How does it work here? Sorry, I'm a Mac user too. So okay, I won't try to find the connection between Daniel and me in this talk here now, because it's a completely different world I want to introduce to you. It is the world of the European funding schemes, the framework programs of the European Commission. Some of you might be very familiar with them, like Caroline Wagner is, but I guess not all of you. You see here what they are. They are the big funding umbrellas of the European Commission to fund research in Europe, and they contain all the funding policies for science, technology, and innovation in that area. And you can look down there. We are currently in the program, which is surprisingly not called the eighth framework program, but Horizon 2020. This is very much money we're talking about. You see here the budgets having increased tremendously over the years for these research funding programs in the Commission. And the new funding program is about over 70 billion euros. The Commission spends on research in Europe, about which 9 billion go to ICT and communication technologies solely. This is the area I want to talk about. I want to present to you a study we did for the European Commission to evaluate the funding policies of a specific area, and that is the area of information technologies and communication technologies. The Commission is structured in so-called Directorate Generals, and there is a special one dedicated to ICTs, and they have an evaluation unit looking after each funding cycle about the success or failure of their funding policies. And of course, what they want to know is not only what was the impact of the funding policies in the current framework program, but what they want to know is what can happen if we change policies for the next funding cycle. And that is the study we got awarded about policy modeling. They wanted to see impact assessment for the 7th framework program in the ICT domain, and what they wanted was ex-ante evaluation, that is EU jargon now, in the full, for the new funding program for Horizon 2020. They are doing this since long, this evaluation unit of the DG INFSO, the DG Information Society and Media, using social network analysis. You might have seen very often these pictures. This is the funding program 7 in the area of ICT for a specific funding instrument called Coordinated and Support Action. And what you can see here is all the organizations funded in FP7 and the projects they have had with each other that are the links between the bubbles. The bigger the size of the bubble, the more projects an organization had in FP7. You can see, for example, the Fraunhofer Society, that is the big green bubble in the center. They are a very big actor in the 7th framework program. The European Commission holds all the data about funded organizations and funded projects, and then you can evaluate the structures they produced with their funding strategies. You can compare this network to the network produced under the 6th framework program and look at it, who is central in this network, what type of network structures produced what type of output in terms of publications and patents, who are central, like the Fraunhofer Society here, who are the hubs in the European research area. What about new member states? There are permanently new member states coming to the networks. Are they at the periphery, or are they managing to get into the center of the network? What about the small and medium enterprises? There's a big tendency in the EU policies to get them into the research networks with big expectations attached to that. If you look at these networks, did they manage? So where are the SMEs in this network? Are they central actors or not? Then you can, of course, run all types of network measures on these structures. How dense, cohesive is the network? What about new entries? Can they attach? Can they get more projects in the next funding cycle? Or are they one-time contributors? And so on. So impact assessment using social network analysis is a kind of standard procedure of these Directorate Generals, and they do it for each funding cycle for their specific thematic area. It is possible to do this analysis as a social scientist because they hold all the data. There's a database kept by the European Commission called CORDIS, where you can see all the funded organizations and funded projects with very detailed information. Problem is, CORDIS data is really messy and dirty, and if you want to work with it, you have to clean it. And this is the first big step to undertake if you want to do this impact assessment by network analysis. If you're lucky, and we got lucky in our study, you get cleaned data by the Commission themselves. So the evaluation unit of DG INFSO provided us with a clean data set on ICT and FP7, and this is what it looks like. It holds many data points on funded projects, as you see, on participants, on participations, because many participants participate twice, and so on the different funding schemes, and so on. So that is what they usually do. But what it is now about the policy modeling, there was a certain dissatisfaction after already the 6th framework program, but definitely after the 7th, because they said social network analysis gives you just a snapshot, a structural perspective on the funding landscape. The actors, the processes, the causes producing these structures remain in the dark. And the evaluation people, the policymakers at DG INFSO, they wanted to see what produced these structures, and they wanted to know what would be the appropriate access points into these processes to change these networks for improvement. So that is why they said social network analysis is a nice tool, but it is not enough. We want to see the future of these networks. We want to see their dynamics, and therefore we need to know the processes and the causal relationships. So they had a workshop in this evaluation unit, and they came up with an idea. What we need is policy impact simulation. So that would be to get the networks going, to see the evolution of the networks, and these driven by the processes on the actor level. This call for policy impact simulation was very urgent because the new funding program was already in the make, and the DG INFSO, they had questions and they wanted answers to these questions. So first was, first I tell you, it was not so easy to get the questions out of them. Some speaker from this morning said, yes, sometimes you have this confirmation bias and you put a question and then you get the answer you think is right. This was definitely not the case in this study. We had a stakeholder board and of the policymakers, and the first 2 months of a 12-month study was spent on finding the questions in discussion with our clients, so to speak. This is the list which made it in the end. There were candidates which could not get through because we could not answer all the questions. The first was, what if they would go on as before? Same policies in Horizon 2020 as in the 7th Framework Program. Second question about technology push. What if they change the thematic areas that will get funding in Horizon 2020? Third question about big or small projects to be funded in the next funding cycle. Fourth question, they would nearly double the funding. Would it be really worthwhile if you throw more and more money on the structures, or would it just produce more of the same? And last question about the favorite child of the Commission, the small and medium enterprises. What if they would manage in the end to get these technology intensive high potentials into the European research area? Would it really change the scene dramatically? So these were the questions, what they wanted to do in terms of new funding policies in Horizon 2020. We got 150,000 euros and 12 months time to answer these questions, which is not much in both respects. The good thing was we had already a simulation platform to use, which was only to be adapted to the study scope. You can look it up on the web. It has an own web page, the SKIN model, which is short for Simulating Knowledge Dynamics and Innovation Networks. The two guys at the top are my two co-developers in that. It is Nigel Gilbert from the University of Surrey in UK, and Andreas Püker from the University of Hohenheim in Germany. So the SKIN model, by the way, is for free. It's open source. You can download it. There are over 40 groups worldwide working with it, and it has a bibliography and so on. So please browse the webpage if you're interested in what's in there. As you have seen, it is called simulating knowledge dynamics in innovation networks. So actually the SKIN platform is about innovation policies, but there are also applications for industry policy and for science and research policy. And the last we needed for this special study for the European Commission. And this adaptation was already done in a previous project, the EU project NEMO, which is short for Network Models, Governments, and R&D Collaboration Networks, and which already adapted the SKIN model to this world of the European funding programs. Because that is what the model has to do. You can imagine, SKIN is an agent-based model, that all the organizations which I showed you in these networks had to go onto the computer as agents. So the SKIN model has agents, research organizations like university departments, research departments of large diversified firms or the SMEs. And these networks, these agents, they do what actors in the European framework programs normally do. So it starts at the left corner there at the top. The European Commission calls for proposals. There were 9 calls in FP7, and we had data on all of them. There are certain eligibility criteria, and if you're lucky, your proposal, which you put in as a consortium, will get funded, and you can start your project. You exchange knowledge, you create new knowledge, you create publications, patents, so-called deliverables for the Commission, you produce output. So the agents in this application INFSO-SKIN, the application for the DG INFSO, contained all the agents out there in FP7 and was calibrated by the data we got from the Commission. And the causal relationships and processes were informed by the research done in the NEMO project before. So when you then look at what the model produces, the first thing you get is a comparison between the empirical data you have and the simulated data. And then you can see whether the model is able to reproduce the database without any question asked so far. And here you can see the output parameters our clients chose, namely the participants, the proposals, the projects, the knowledge flows, and the network indicators. And you can see in the second column the empirical data for a specific funding instrument, small projects these are. And you can see in the last column the simulated data for these indicators. The blue ones, there you see that we had no empirical data for that. Number of proposals is actually possible to obtain from the Commission, but for example, knowledge flows, learning between actors, creating new knowledge, you cannot observe that. This is why we did not have any empirical data, but the simulation model, of course, produces such. So that is the workflow. Now you're confident that the model is able to reproduce the database and can be extended without any changes into the future, which we call the baseline scenario. You can then ask the questions. You know all the what-if questions our stakeholder had in mind. And just to show you 2 examples for results, this was the policy background for the technology push question, the thematic change question. You see here a quote from the green paper of the Commission, and the stakeholders actually wanted to know, what if we don't continue to fund these 9 thematic areas? If you are drastic, you say, we only fund smart cars in the next funding cycle. That would be really drastic. They didn't do that, but they wanted to know, what if we change thematic areas? And these are the types of results you get. You get, you see on the y-axis, the knowledge flows as an output indicator. You get many output indicators, of course, knowledge flows and over the time of the funding cycle. And the red line is the baseline scenario. So reproduction of the database, continuation into the future without any changes. And then you simulate what happened if we fund more themes and fewer themes. And that was actually a big surprise for our stakeholders because they had thought that this would create big trouble to the networks if they do that. But as you have seen in the graph, the change is not too drastic. And they discussed how drastic actually this picture is, and they decided not so much, and that it is actually a political decision whether they fund fewer or lesser themes. The networks in the European research area are pretty stable and are not prone to a disaster if they do that. The last question I want to show you a result for is the one about the SMEs. So this question was not about why SMEs do not participate in EU research. There are various reasons why they don't, and it was not our task to investigate that. Our task was to simulate what would happen if they indeed managed to get the SMEs into the networks. Because there were heavy criticism about the SME policies. In the stakeholder group, they said, don't put so much effort in this attempt to get the SMEs in. It will not change the world. But when we simulated that and looked at all the output parameters, we could see indeed it changes a lot if you manage to get the SMEs, the high potentials, into the research network. So it was a supporting argument for the policy to try everything to get the high technology SMEs into European research. So it supported very much the SME policy advocates in the stakeholder group. Yeah, what you can do with this type of thing is you can actually not predict a state in the future, but you can give certain indications about more likely scenarios, about trends, what will happen if, under certain conditions, you change parameters, and so on. And you can look, very interestingly, at some type of unobservables, empirical unobservables, like learning and knowledge flows, because your simulation will produce data for that. If you want to read all the details, there's a publication out in the Journal of Artificial Societies and Social Simulation. It is so late because the Commission did not permit us to publish right after the study. So they said they wanted to make policy first before anybody could see which type of knowledge went into the decision making. So after 2 years, after presentation and approval of the final report of the study by the European Cabinet, we were allowed to publish. That is why it is out just now. This is my last slide. With this methodology, further projects are running in the moment, like, for example, another EU project looking at the role of civil society actors in European research and how they changed the landscape. You might have realized there are now stakeholders like museums, the police, city councils as funded partners in European research. How do they change the research landscape? That is the question of the simulation done in the GREAT project. And the last project is about a simulation of the German research landscape to find out about the innovation potential of public research organizations like Max Planck, Fraunhofer, Helmholtz, and Leibniz Society Institute. German government funds all these guys with heavy money, and they want to know what they actually produce and what they could produce under certain conditions. Thank you very much.
Okay, thank you, Petra. And the last speaker for this session is Ben Shneiderman. He is the Distinguished University Professor in the Department of Computer Science at the University of Maryland, where he was also the founding director at the Human-Computer Interaction Lab and a member of the Institute for Advanced Computer Studies. I think he is best known as a pioneer of human-computer interaction and information visualization. However, today he is going to talk more about event analytics. So,
thank you very much. Appreciate being here, and bravo to Kadi Borner and team for bringing together a really interesting interdisciplinary community of people. From those who are here, there are only about a half dozen who I knew before, like Wendy Hall or Bill Rouse and Sandy Pentland. My collaborator Scott Dempwolf is here. But people come from very different areas, and they all share an interest in trying to understand how science, how technology, innovation, engineering, design emerge, how research results get done. And then they're also interested in acting. They're interested in taking a role and how, as Petra described, the European Union might have changed their approach to funding research, and similarly how the NSF or other groups in the US might. I'm happy to represent the Human-Computer Interaction Lab at University of Maryland, an interdisciplinary community that is really founded from computer science, my own background, and information studies, but has many other bridges, including the wonderfully titled Maryland Institute for Technology and the Humanities, MITH. Our website has 750 papers and 200 videos, 40 pieces of software, and so on. So I couldn't resist to proudly show last week's publication of the 6th edition of Designing the User Interface, my book that captures the idea of what's happening in this field, and that's where I come from, and it includes the notions of visualization, which have been, I think, the most strong, commercially successful efforts on our part, and really leads to the contribution that I want to show you today. The notions of visualization go back to the multivariate kind of data, and Daniel McFarland and Petra gave me great examples to start from, because they showed these multivariate data sets as scattergrams. They showed time series data. They showed network data. And all of those are part of that way in which we explore data. And I want to show you a new tool today. So my goal today is to sell you at a very good price, a tool for doing new kinds of analysis that I hope will shed light particularly on these innovation trajectories. I became interested in this because of the book that I mentioned here earlier, The New ABCs of Research, published earlier this year, which took me down the road of trying to understand what led to high-impact research. Now, this is a challenging question, not just in science, but also engineering and design. First, how would we measure high impact? And then, what can we do to change the way we do research as students to get higher impact? But my message today is really the funding agencies, business leaders, academic administrators, and how you might be able to change the impact of the research that's done in your community. I think there's a bit of a model in there too, and I will leave it for another time to discuss, but I go back to Scott Dempwolf's previous work about network modeling, very much like what Petra showed. This was our earlier work on Node XL, which has now 500,000 downloads and widespread use as a network analysis tool. And I'm rather proud of this strategy, which uses tree maps, the idea that I'm also the source of for hierarchical data, and groups the largest cluster in one place and then the other ones down to the smallest ones here. This shows regenerative medicine communities in Howard County. So Johns Hopkins University and University of Maryland are large players, but there are key companies like Martech Biosciences and Osiris Therapeutics, and you quickly can see them. So good design of networks and visualizations, not just these blur of clusters, are what I think provide insights. And that was the work that we were doing that Scott led me to in terms of understanding how networks work in the world of innovation. And one of Scott's efforts was in the state of Pennsylvania. Here, 11,000 nodes in a very beautiful layout, beautiful but not very useful. It's extremely difficult to make sense of these kind of layouts, and I caution you when you look at a network, don't go past the beauty and take a look at the value and the meaning. Now, applying Node XL and the group in a box, we can break out about 65 of the communities, and focusing on the largest ones, we immediately see that the key one in Pennsylvania were pharmaceutical, and there turns out to be 2 individuals, each with about 100 patents, occasionally work together, that are the key people. In Pittsburgh, the Westinghouse Electric Company was the center for the innovation hub and community there, and other key ones through the state. So my point is, you can go from that uninformative but maybe good piece of wallpaper to something that's maybe less charming but more informative. And I asked at one point Scott for show me something about Maryland, not Pennsylvania. And so he did. This is for the Human-Computer Interaction Lab. These are the people at Maryland in that lab and their partnerships with colleagues at University of Maryland, Baltimore, with other groups around the state, and these are all from NSF data that shows co-authorship. So networks can be helpful, but today I'm here to say let's get beyond networks, let's get beyond multivariate, let's get beyond time series. Oh, I had one more beautiful slide from Scott's work in Illinois, which showed the innovation networks for economic development, how universities partnered with various companies, which ones were important, and so on. So, okay, so I'm moving on now to the study of what I call innovation trajectories. Now, we had begun studying the work that we had done, 25-year innovation trajectories for a variety of particular visualization technologies, and we came to understand that the way to look at this, we thought, was think of the history of these events as a series of point events and intervals. And this is what came actually from our development of EventFlow, which was designed for patient histories, electronic patient histories. Imagine a person's 100-year lifetime with some 10,000 medical events of physician visits, of symptoms, of treatment, where they're taking medications over a 6-month period, or under hospitalization, or diets, etc. So it's a huge volume of data that's usually difficult to make sense of, but EventFlow proved to be valuable. We now have 40 or 50 research groups who are using EventFlow, mostly for electronic health record histories, but I'm going to try to say that they are valuable for innovation trajectories. So what we're looking at is what inputs produce desired outputs. That's kind of the basic story. What forms of money, what kind of people, what kind of institutions, what kind of starting points produce the kind of desired outputs, which could be a successful PhD, a product that's launched, a future professor, and so on. And, you know, for the world we were focusing on with the data set that Scott was studying from medical data products, patents, grants made by NIH, company launches, or product launches, also clinical trials and other kind of efforts I'll show you. The first step turned out to be descriptive statistics, usually a boring, simple starting point, but since nobody really knew anything about how long does it take on average to go from a patent to a product? How long does it take for a clinical trial to produce an FDA approval? What are the relationships? Okay? And so this leads us down to temporal models of event sequences, not time series, but categorical time stamps. And then we want to go down the road to hypothesis testing, where from the data you can test hypotheses. Did those who get small business research grants have a better chance of producing a product than those who didn't? Did early patenting lead to successful products? Did having 3 or 4 or 6 patents have a higher success rate in producing products? Those are the kind of questions, and here that leads us to the action items. When should SBIRs be granted? Should the NIH wait till a company's been formed, till a patent has been applied for? Do patents actually lead to successful products, or can you have products launched without patents? And then, do partnerships, this is my important question, Lynn Zucker's work also reflected on this, do partnerships with academics, of industry academic, do they make a difference? Should they happen early? Should they happen late? Okay? Now, you know, my thesis from the book was that upstream partnerships were really the key to success, that early partnerships which continued between academic researchers who brought a theoretical perspective and industry people who had a real problem, and that was the formula for continued success. Okay? So just to give you an idea of what this looks like, here is an example with some medical data that shows 90 patients at once in a very simple case. They either arrive at the hospital, go to the emergency room, those are events, go to the intensive care unit, get sent to the floor, a normal hospital bed. They may die or they may be discharged. Those are outcomes. And here we're only looking at point events, not intervals. And the way the summary shows it, the most common pattern is these 26. They come to the hospital, go to the emergency room, and within a few hours they're released. The light blue line is they're released and they're alive, and that's 26. Now, time goes this way. Some patients, they arrive, go to the emergency room, the red line is the intensive care unit, and then after, on average, 5 days, they go to the floor of the hospital, and on average, after 10 days, they are released. Happy news. Some take a little longer, some bounce back to the intensive care unit, and some may even take, you know, a whole month in the hospital till they're discharged. And sadly, some may wind up dying. The black point is the outcomes, the unhappy outcomes of those who died. But this very simple example shows you a small number of medical events and 90 patients. We've done as many as 200,000 patients in this kind of analysis, so it does scale up to a point, has its limitations. I think I'll skip those and just go straight to the innovation events. So in the data set that Scott's been working with, there might be a formation of a company or a partnership, might be a series of patents over time, there might be FDA approval, might be a product launch, small business initiative, research, small business, help me, IR? Innovations, research, thank you. And then, or there might be a clinical trial that lasts 2 years or 3 years, and maybe a product launch comes after that, or FDA approval. So this might be the kind of data we had, and we've attempted to extract it. And as we start in new areas, the first lesson is the data is messy. Data is incomplete, data is compromised in many ways, is erroneous. I could spend a long time talking about all the errors, but let's look at just a little bit to give you an idea. Here is from patent application to final FDA approval for 26 products. So these were 26 products. So only 26 that Scott was able to find in his NIH database that had a patent and then also had FDA approval. And it took a minimum of 3 years, but some of them, sometimes it took up to 20 years, and this is the distribution of time. You can see the individual streams. A lot of products have many patents and before they get FDA approval. And you can readily scan the individual ones, and here with 26, you can see almost all of them on the screen at once, but you know, with 2,600 or 26,000, the tools we have for aggregate view and organizing the data become very powerful. So you can see the way we represent the information in very simple ways. And for academics, we've also done graduate student histories. They may publish a paper, they may take certain courses, they may go to have an internship, then they graduate, and they may go to be an academic in Dan McFarland's version of history, or they may go to industry research, or they may go to postdoc. And so we can see the trajectories for different people, and we can see whether going for industry internships led to a higher probability that they would go to a research job or go to a teaching job. Okay. Here is a larger set of 844 drugs from the FDA Orange Book, and again, looking just at a simple distribution here from first patent to FDA approval, so you can see how you can readily see the path. And this was another case of medical devices, so we began to explore those, the relationships of clinical trials to FDA approval, and the time from the start of the clinical trial to FDA approval was on average 7 years. So it began to reveal those patterns. Now, this begins to be the more kind of complex analysis that EventFlow lets you do. So here's 34,000 medications, and you begin to see the key, and we have these 4 items here. The key pattern here, about 15,000 of them, are there is a research history, and a patent occurs somewhere in the middle of that history. And we can look at the distribution of those. Sometimes the research includes no patents, but it has a clinical trial as part of it. Okay? And so you can see these different patterns. Here's the research, which later leads to a patent. And here's a case of patents. Very few cases where there's early patents and then research results after that. You get this funny thing, stripe stands out. And that's the power of this kind of visualization. You look at this zebra stripe over here, and I asked Scott, what's going on over there? So here you have these repeated FDA approvals in the database, but no research, no patents, no clinical trials. And so there's funny things in this database that need to be cleaned up if you're going to try to build any kind of model or understand what's going on. And so the beauty, I think, is to be able to see common patterns, rare events, exceptions, and the general flow. We've been constantly pleased by the 40 or 50 research groups where they consistently come back. Two groups at University of Maryland, Baltimore that were partners. Within 6 weeks, one group working on radiation treatment for prostate cancer and the other about warfarin treatments for minimal brain trauma. Both of them in 6 weeks were able to publish new results because now they could analyze the temporal sequence of data. So what I'm here to, offer is the sense there's a new tool here. I don't have results to tell you today. I'm just showing you the early stages of use of this tool. This is work supported from the National Science Foundation with Scott Dempwolf. And we think there's an opportunity to develop new theories based on what we can now understand about temporal sequences, which kind of events and inputs produce which kind of outputs. We do see the first initiative is promoting data quality again and again and again. I can't tell you how many times where people have been doing mathematical modeling and statistical tests and machine learning on data sets, and they have no idea of how bad the data is. And seeing the data tells you a lot. And so even if you do nothing else with the visualization, just take a look to understand how the data is organized and how surprising it is. I dare to say that we could come from this by proposing causal models. Very difficult to take on philosophically. We're constantly pressured to do those kind of things to get the kind of prescriptive advice that agency funders would like. And then more, you can see sometimes how one thing causes another more reliably, but to understand, as I probed with Lynn Zucker, why is it that you think that academics working with industry produce higher impact results? What's the driving mechanism? Those are deeper questions for which no easy statistics will give you an answer. You have to probe more deeply to understand the underlying issues. And then we are already doing comparisons of cohorts. The successor tool for EventFlow is called COCO, for cohort comparison. It's PhD work of Sana Malik, who defends her dissertation next Monday, but she has now 5 successful case studies of groups, some of them medical, looking at 2 cohorts of treatment and being able to find statistically significant differences between every possible pattern of comparison of frequency of events, duration of events, repetition of events, and that's opening up new possibilities. And we're pleased that some large companies have already licensed and are looking to take these ideas and make them more widely available. But for now, we are a small community at University of Maryland, so I have to say thank you to my collaborator of many years, Catherine Plaisant, the predecessors of this work, these great students, National Science Foundation's funding for this current piece of work with Scott Dempwolf on visualizing science, technology, innovation, activity, and sequences with EventFlow. Come join us in College Park on May 26th for our 6th annual EventFlow user group meeting. and hear the kind of stories that our medical and other researchers are telling about how they can now probe data in different ways than the traditional multivariate time series and network kind of models to be able to understand and then act in serious ways for science policy. Thank you.
You mean the outcome of the projects, or? Yeah. No, that was not the end of it, no. Of course, the expectation was that there is a relation between network structure and output in terms of output quality, but also in terms of output quantity, because one of the big objectives of the funding policies would be scientific excellence of Europe in comparison to you guys and Asia. And the question was, what type of network structures in the European research area would improve outputs in terms of publication quality and quantity? Yeah. There's an innovation component to that as well. So that was a question for the spin-offs of multinationals and of universities and so on. Yeah.
Julie Mason from the National Cancer Institute. My question is for Daniel. Thank you for sharing your fascinating data with us. In your model, success is measured by the production of a long lineage. And I have a two-part question. One is, what kind of decisions do you anticipate making based on the results from the model data? And secondly, do you have any plans to include other career paths that go beyond the academic route, since you noted in your discussion that only a small proportion are producing progeny, and we know that there is a lack of academic tenure track jobs available?
Sorry, technology challenge, surprisingly. No, that's a good question. I mean, in terms of the data limitation, we don't have information on the people who exit academe. NCES survey data apparently has that in the restricted form, so we're trying to get that and link. But the prior research suggests that a lot of women in STEM are picking jobs in industry over academic posts. And it's not, I mean, there's a variety of different pieces out there I've seen on that might afford, like Kirsten Bunker's work at Oregon would give different narratives for why. But I think the argument that we had in terms of success, or at least reproductive success, is that fields expand and the representation of women in those fields expand on the basis of their likelihood of becoming faculty and having lots of advisees who become faculty. And so it's just thinking, that's one metric, and there are others, but I do think it's a reasonable one. That said, I mean, right now at Stanford we have this current problem, which is that a lot of the faculty and top students are getting picked off by industry, and somewhat of a crisis to a degree in terms of the best students not staying behind to train future students, but instead going in industry and doing partnerships and non-disclosures and a variety of other things for a variety of other reasons, for wanting to have greater impact and other reasons, not thinking tenure is so great, or seeing the endless postdoc as not desirable. So there's all kinds of different positive, negative stories we could put there, but I don't know for sure on that one. So.
Yeah, can I follow up on that? It's sort of a complicated question, but the simplest way to say it would be, one of the things that generates, if you will, the kind of postdoc problem or the problem of reproduction and so on, is that if you're a really good researcher, we tend to think of the students as outputs, but remember the students are also inputs. And that if I'm a successful researcher, I will get lots of grant money, which means I need a lot of help, right? And I'm going to hire lots of graduate students, and there's huge variation in the size of labs, right? One version of this story is, and then the issue comes like, how can I very intensively train 40 students, right? I was at a graduation at Georgia Tech, it was a big engineering school, and there was a guy who like about every third student came up, he walked up to hood that student, and we're like, who is this guy? And he was in aerospace, I think. And so one of the things that might be interesting to look at is the size of my progeny and what happens to them, right? Which is to say, a lab that generates lots of students, are they generating, if you will, lots of sickly students who don't reproduce well? And if I have a very small number of students, do I nurture them well so they grow up strong and virile? Or some other way, right? I mean, you could imagine a lot of rival hypotheses. So I was wondering if, the first version of that, since you measured the number of students that I generate, when you take it to the next generation, is there any correlation between how many students I generate and how successful my students are compared to somebody who generates either more or fewer?
That's a great question. We're currently trying to measure that. And once you have this data set, you start to try to generate metrics like, do you have the same gender advisor or not? Does that help your chances? Are you in a field that has high demand or low supply? So we're modeling things like that. In addition, there's do my progeny, are they like clones with a half-life? You have those kinds of, I use colorful language, but I don't, just so I keep my head straight in terms of what's going on in the models. But I think that's the kind of stuff we're exploring, and we're early because we only have 30 years of data. We haven't linked up to, so you only have like 3 or 4 generations if you think about it. So we're trying to scrape back to the 50s right now. And in addition, we're trying to link up to other data. The things we don't have is like the productivity of these students, which is an obvious characteristic. And an economist in the audience would say, where's the GRE scores? Because you have selection. And so we're trying to fill out I think the main point is we're trying to fill out a high quality data set. And so we're in the early stage where the fact is that we already have a better data set than we think anybody else has, but we need to make it better to ask and answer the questions that are important. And I think that's where we're trying to go, and it might be a few more months or a year before we fill it out. But these are exactly the directions that both questions we want to go, and we're trying. It's slow.
You're dealing with an ongoing trend of dramatic growth in non-tenure track teaching faculty nationwide. And so non-tenure track faculty typically can't buy PhD.
Right.
And so, it's gone like
Yeah, other things say that the biggest growth is actually staff. But no, these are, again, we only know who's in these corpora in terms of their traces and their histories of because we're not surveying people. This is big data and it's found data, so we have to be a little careful and focus on what we can and can't say, but obviously.
It doesn't like but it does build an overall environment. 1/3 of adjunct faculty members in the United States are local.
Yeah. Right, and so we're trying hopefully through NCS survey data, which we're trying to get restricted. They ask every doctorate what their intentions are, where they're going to work, and as long as we can link it up, or even if we could link it up at the program level, which we hope is an aggregate we can do, we can begin to answer some of this, maybe not all, but at least more richly than has been done, and perhaps more temporally in terms of people's careers to date. So that's the goal.
Yeah, hi, I'm Caroline Wagner. I just have 1,000 questions, but it seems like one of the main purposes of all of the things we're trying to do is to encourage the creation of new knowledge that's highly creative and useful in like a Joel Moker sense of useful knowledge. So and if I can put in a plug for myself, in my +1 article on Nobel Prize winners, I found that Nobel Prize winners and their equally elite peers operated very differently in the network. That the Nobel Prize winners were much more likely to reach beyond their close-in networks, have fewer offspring than the elite who didn't win the Nobel Prize, but of Nobel class. They reproduced more effectively, but the Nobel Prize winners were way more creative and way different in the way in which they operated. So the upshot of my question, and maybe this is a question that can't be answered, but I'd like to hear the panel's reflections on this, is how do we tell that we're creating the structure for creative, truly useful research, rather than simply like reproducing ourselves, but we're looking for ways to supercharge ourselves into creative, useful, and highly applicable, impactful knowledge.
Yeah. Wow. You use the term useful, and there's more than one way in which academics are useful. And big breakthroughs that come from Nobel Prize winners are maybe useful, but also many other kind of things are useful. And the ones who may train a lot of graduates but maybe not write a lot of papers are also useful and in a different way. So I think the Becker model from Washington University in St. Louis is an informative, thoughtful, provocative 16-page list of all the ways to measure the impact of a research project. And they break it out into 5 categories, such as basic knowledge, or industrial application, or educational, or public policy. But there are many different ways to be useful and to have impact. So there's a strong movement also to go beyond just science, citation counts, and look not only just at download counts, but other ways that people are useful. And there's kind of the alt metrics. If you look at the website altmetrics, I think it's .com actually, makes us aware that numeric metric, there are many kinds of numeric quantifiable metrics, and then beyond that, to study the work of creative people such as university professors takes a more balanced qualitative and quantitative approach to looking at it. And disturbingly, it's not all easily reduced to a set of numbers from which you can run a correlation or logistic regression. That life is troublingly more complex, maybe satisfyingly more complex. So I guess just the summary is there are many kinds of usefulness. Do you want to respond to that? Or? Well, again, science citation counts, remember the very top ones tend to be methods, laboratory tests that have hundreds of thousands of citations, and they may be important and valuable, but they may not be these big creative breakthroughs. So, and often the real creative breakthroughs may not even be embodied in a paper, they may be in other places. So it's a little bit tricky to say what it is. So there's also, there's another troubling thing about any of the work in this field is a lot of it tends to be retrospective legend building, where people will tell the history of what happened, of look at the Nobel Prizes and what they're given for, but what actually happened. There are several very nice analyses that show that the Nobel Prizes, let's take the one of Arno Penzias and Robert Wilson for the background cosmic radiation, a great fundamental breakthrough about the Big Bang. Actually, they were doing very practical work. They were doing applied research for Bell Labs to build better microwave communication systems, okay? And so they were doing practical results, and the practical benefits were substantial and influential, but when you hear the story, it's about, wow, the serendipitous discovery of background radiation, isn't that great how science works by surprises? Well, it doesn't. I think that's a misinterpretation of the history, and so I've become quite aware of reading these histories a little more carefully and looking at many ways in which a breakthrough manifests itself in changes to education, changes to practice, changes to policy, and maybe fundamental knowledge that inspires others. So these are tricky. There's also the problem of the Sleeping Beauty papers. There was a wonderful presentation a few weeks ago at the Library of Congress about the papers that go unnoticed for sometimes 100 years, and then suddenly they arise and become highly cited. So yeah, Gregor Mendel, 20 years after he died, was first, and then there's many other stories, but, more that documented with contemporary statistics. So life is pretty complicated for making causal predictions here. And I think people should be aware, and what I take away from all this is that we have to be all engaged in telling these stories and listening to each other and understanding the richness. Human creativity is quite wondrous. It just does not lend itself to neatly decomposed models of a few statistical counts. So that's kind of a sobering reality, but I keep coming back to saying a wonderful reality. Just remember the unbounded creativity of humans is a joy.
Yeah, fascinating question, and I think the emergence of a new should be made a point in the trajectory of innovation, definitely. Very often innovation research is about diffusion of innovation, and nobody talks about the emergence of the new, the creative thing which starts it all off. There are very nice studies from cognitive science about creativity. So, for example, that if you give a logical sequence of numbers or letters or words or whatever to people, that most people continue the logical sequence in a certain way, which is possible, but there are other possible ways to continue the very same sequence, and a fraction of people then find a more innovative solution to continue the sequence, and very, very few people find not so easy solutions to continue the sequence. Same true for analogies. Most people, if you tell them a word or a picture, they find the very same analogy to that, and only very few find interesting ones, which are possible as well. And I think this type of research would be good to be connected to the more economics part of it, the more social science part of it, and so on, because it's all about how to handle knowledge and how to combine knowledge in an innovative way. And when I said at the end of my talk that in Europe they now involve non-science actors in the research and innovation process, I think there's the very same idea behind, that you get knowledge sources into the networks which have not been there before and which might be very far apart from the thinking normally produced, and which might distort the landscape. This will challenge traditional peer review systems, of course, because why should these networks containing museums and policemen be evaluated by the scientific community in traditional peer review forms? These groups should be involved in peer review of knowledge production as well, and should evaluate the outcomes. I think that could give the whole thing a push into more societal impact and utility of the knowledge produced.
Wow, you ask a hard. I'll be brief. So in terms of usefulness, it's hard to find the ultimate metric. So I can just tell you what we're doing in terms of measurements of innovation or representation of it. I'm trying to decentralize the individual. The individual has forever been seen as the locus of creativity. And in many ways, we have the capacity to show the community of scholars or the network of scholarship that contributes to a new sub-language or a new, like a new Creole, right, if you would, that can emerge from all these texts and these corpora, and we can follow those. And then we can show whether those new bodies of language or those sub-languages that arise have some kind of relevance to the public in newspapers, to policy in terms of laws, in terms of application to patents, or drug trial. I mean, there are ways that we can see whether these languages get adopted. And I'm a sociologist of science, so therefore I have a very Kuhn-like view of science as being these kinds of thought styles or thought communities that come and go in different eras and have that kind of relevance. Now, in terms of impact and usefulness, yeah, I think in the end you could say, well, gee, there's this bundle of this new language, nanotechnology, or latent Dirichlet allocation, or whatever. And does it have impact and usefulness? We need to find utilitarian or pragmatic returns, whether it's good or not. Like, I mean, obviously I can think of a thought style or community that grows and dies, which leads to lots of death, right? Like military, like not necessarily, I mean, some kind of weapon or whatever. So it's not always the case that we can just punt and be a relativist, I think. But so I don't know what those metrics would be, but I do hear your sentiment. Like, wouldn't it be nice to have some pragmatic thing of all these rises and falls of ideas that some of them galvanize more broadly, but what's the ultimate value to some extent for society? And maybe we have to come up with some collective utility as opposed to individual utility, but a societal maximal utility function that we model. And I don't know, but that would be one idea. Hope that was short.
Okay, so
I just wanted to congratulate Petra and Ben for actually offering to try out their models. So the SKIN model is on GitHub, I just checked, and it's well documented. And Ben invited us to his workshop. I think we need more of this. So if any others of you have models that can actually be tried out and be downloaded and be fed with new data, or if you can share data, I know many of us cannot share data, but some data sets we actually do share widely. So if you have pointers to data sets and to models and also to visual analytics tools, please do inject them into the Twitter feed surrounding this conference, or send them directly to me and Dan, and we make sure they end up in the workshop report, in the report for this conference. I think it would be wonderful to have a list of data sets and models that can be used and are ready for action. Thank you.
This is a pretty extraordinary panel in the range of representation of, at least for Europe and North American knowledge creation. So my question is to extend a couple of comments that surfaced just a few moments ago to ask about models of knowledge creation and the kind of general patterns that you are observing. I'm very curious about the emergence of design as a valued activity, as parallel to scientific knowledge creation, and of hybrids such as the Canadian model of research creation, which is now a very big driver of the Social Sciences and Humanities Research Council. Similarly, I'm very struck by the extraordinary kind of energy politically being placed on industry-academic collaborations and those kind of broad outcomes, and the lightening of emphasis on blind peer review and pure scientific valuation. I wonder if you could make any comments on those two kind of rapidly emerging bodies of hybrids.
Well, oh boy. I'll pick up on the design thinking because that's become a powerful theme for me, which, I mean, I started as a traditional physicist, mathematician, scientist in the age of Thomas Kuhn, and that was what research was. But engineering became part of research. Here we are in the National Academy of Sciences, 1864, but the National Academy of Engineering, 1863. The National Academy of Engineering only started in 1964. So engineering as research is a newer topic, and the National Academy of Design doesn't exist as yet, but I've proposed it for the year 2064. But the movement of design as a central way, design thinking of gaining new knowledge is on the upswing. And the data I have, if you take a look, it shows that after 1975 in the New York Times and also the Google Ngram data set, design exceeds science and engineering in terms of its mentions. So there is something deep going on where design thinking has become, and it's not all Steve Jobs and Johnny Ive, but there's a general movement that is lifting design, and I would say if we look down the road, it's time for a National Academy of Design. So.